Good evening, everybody. Today we are going to discuss shortcut methods for Fourier series for PWM techniques, multiple PWM technique, and also we will discuss the sinusoidal pulse width modulation. That is the last topic in pulse width modulation control. Right. In the last class, we already derived one equation for four pulses. This is the four pulses per half cycle. For this, what is the derivation? This one. So this much of lengthy equation will be there. So whenever you are implementing within less time, so then at the time this will not be suitable. So then we will go for the shortcut methods. And here for this equation for V01, how much we are getting? 86.025. Just remember this one. Now how to implement this shortcut methods? See, the Fourier series you already studied in first year or second year in your BTech level. So the same thing I am discussing here itself. Here I am writing, I have given each and every properties, all those things. Right. Now here majorly we are focusing on odd plus half wave symmetry as well as odd plus quarter wave symmetry. Because till now, if you take any waveform, what we got here, always we are finding only Bn. So that's why more focus we are going to keep on odd plus half wave symmetry as well as odd plus quarter wave symmetry. Right. So this is odd function. For odd function, what happens? Bn only will be present. An will be absent. Right. So here odd plus half wave means what happens? Only Bn will be present. But what is the condition for odd plus half wave symmetry is f of phi is equal to f of pi plus pi. Right. So this condition must be satisfied for half wave symmetry. For quarter wave symmetry, odd plus quarter wave symmetry, what is the conditions? F of 90 plus phi is equal to f of 90 minus phi. Or you can check f of 270 plus phi is equal to f of 270 minus phi. So that means whenever these two conditions are satisfied, then you have to go for odd plus quarter wave symmetry. Whenever you are going, satisfying this condition, right? Odd plus half wave. Now, if you observe these two, what is the difference? See here, what is the formula for odd plus half wave symmetry? Bn is equal to 2 by pi, 0 to pi, f of t sine n omega t d omega t for odd values of n. Here they are using h term, I am using n term. Okay, so here what are the limits? 0 to pi by 2, right? For odd plus quarter wave, what is the limits? 0 to pi by 2. So that means if you are getting odd plus quarter wave symmetry, the derivation is very simple. So if odd plus half wave symmetry, a little bit lengthy, but compared to the earlier what we have derived, so compared to that one it will be better. So when if you have less time is available, so it is better to use this shortcut methods, right? So now the same waveform I am considering, so which is nothing but 4 pulses per half cycle. So now what about this waveform, whether it is odd plus quarter wave symmetry or odd plus half wave symmetry, that is most important. What is first of all here quarter wave symmetry? What is the condition? F of 90 plus phi is equal to f of 90 minus phi. Now, if you see this is your pi by 2. So this is your pi by 4. This is your pi by 2 plus gamma minus d by 4. Therefore, exactly this is pi by 2. Therefore, this is pi by 2 plus theta, and this is pi by 2 minus theta. Therefore, because of equidistance, we can say that is a quarter wave symmetry. Next, again, this is 3 pi by 2. So this is 3 pi by 2 minus theta, and this is 3 pi by 2 plus theta. So therefore, because of both conditions are satisfying, we can say that this waveform is odd plus quarter wave symmetry. For odd plus quarter wave symmetry, just now we discussed that Bn is equal to 4 by pi, 0 to pi by 2, f of theta, f of t, sine omega t, d omega t. See this. So for odd quarter wave symmetry, 4 by pi integral 0 to pi by 2, f of t, sine n omega t. For odd plus half wave, what happens? 2 by pi and 0 to pi. So that is a difference, right? So now here we are focusing this one, right? So every time we are going only for this one. So 0 to pi by 2. See, from 0 to pi by 2, right? We have to solve only up to here. So that means this much of pulses we already ignored this. Understand what I am saying? So this is the thing I want to tell you the advantage if you use Fourier method shortcuts, right? But in the academic examination, sometimes let us say explain multiple pulse width modulation control means if you use these shortcut methods within 2 steps you will get the answer. But if they are asking for 15 marks question, then it is better to use the previous procedure, right? Or if there is no problem, then you can go for this procedure. I'm giving both methods. So which one is flexible based upon the marks they are giving? So just go ahead. So now here Vn is equal to 4 by pi integral 0 to pi by 2 f of t sin omega t d omega t. That means from here to this middle point we have to apply. So that means what happens? Only 2 pulses is enough. From pi by 4 plus gamma plus d by 4 to pi by 2. This is pi by 2, right? What is the value? Already it is 0. So no need to apply. So you just apply up to this point only. Okay, right. Therefore, so I'm using here, what is the function f of t is nothing but Vs. So 4 Vs by pi, what is the first limit? Gamma minus d by 4 to gamma plus d by 4. So gamma minus d by 4 to gamma plus d by 4 sin n omega t d omega t plus gamma plus pi by 4 plus gamma minus d by 4 to pi by 4 plus gamma plus d by 4. That is this one. So now if you integrate this one, right, and after the limits you will substitute, what you will get? 4 Vs by n pi 2 sin n gamma sin n d by 4 plus 2 sin n pi by 4 plus gamma sin n d by 4. So in this you just take 2 sin n d by 4 common, because this term is printed in both terms, right? So that's why if you make it common, if you take it outside, you will get this one. And finally sin n gamma plus sin n of pi by 4 plus gamma. And what you will get? 8 Vs by n pi sin n d by 4 sin n gamma plus sin n of pi by 4 plus gamma, right? So whatever we have solved earlier, the same problem I have taken. If you want, you please refer my previous video. So now I am taking the same values. Vs is equal to 100, d is equal to 60, and gamma is equal to 22.5. And substitute the values here. And I am going for only this one. And finally, what you are getting? V1 is equal to 86.6. This is nothing but your V01. Both are same. So V01, what I got here. So V01 is equal to 86.025. Right. So now this, from this, what I am getting here again the same 86.64. That is nothing but V01 magnitude peak value. So in this way you can solve this whenever you are having higher number of pulses. Shortcut method is more flexible. Okay, right. Next, just I am giving 1 or 2 examples. Now this waveform, if you observe this waveform, first we will check this quarter wave symmetry. See, this is 90, this is 180, this is 270. Right. Now if you take, this is 90. 90 minus f of 90 minus theta means this one. F of 90 plus theta means this one. Right. So if f of 90 minus theta, if you take here, what happens here? Some magnitude, lower magnitude is present. For example, if you take some value here, some magnitude is present, positive magnitude. So this magnitude and this magnitude both are not same. See, this is 90 degrees. Let us take this point here. At this point, what happens? Your magnitude is lower. Take here point, some magnitude it is higher. So therefore, f of 90 minus theta is not equal to f of 90 plus theta. Similarly for 270 also. So that's why we are calling this one as odd plus half wave symmetry. Next, quarter wave symmetry. Let us take 90 here. This example. This is 90 here. Therefore, 90 minus theta is equal to 90 plus theta. See here, 90 minus theta. That means this is just an example. This is theta, means this is 0, and this is also 0. So because of this one, you have to go for this quarter wave symmetry. But here it is not possible. If you take here this theta, here lower magnitude, here higher magnitude. Magnitude is not same. So that's why this is odd plus half wave symmetry. But f of phi is equal to f of minus of f of pi plus phi. Right. So here this is f of phi means this is minus of f of pi plus pi. Okay. So that's why it is odd plus half wave symmetry. But here 90 minus theta is equal to 90 plus theta. That's why it is quarter wave. Now again, one more waveform. See this one. So if you take exactly this one, this is theta means this is 0. This is theta means this is 0. So for example, if you take theta is here. See over here, whatever the magnitude is there, here also you are getting the same magnitude. So therefore, at this instant, if you take the theta here, 90 minus theta is same, as well as 90 plus theta is also same. So then you can go for odd plus quarter wave symmetry. That is nothing but Bn is equal to 4 pi pi integral 0 to pi by 2 f of t sine in omega t. Understand? Right. This is very important when you are going for PWM techniques, right? Because see, you already seen in multiple pulse width modulation techniques, for 4 pulses it is very complicated to derive it. But if once you know the shortcut, it is very easy. Okay, that already shown you and proved also. Now, whenever the signals are going to be changed, right, then you just use this concept, right? Okay. Next concept, pole voltages. When you want to go for sinusoidal pulse width modulation, this pole voltage concept is required. So very simple, right? First of all, this is switches S1, S4, S3, S2. That is nothing but simply bridge inverter. For bridge inverter, how many switches? 4 switches are there. These are the 4 switches, right? So here I will tell you when the switches are on and when switches are off, what is happening. So first, what is meant by pole voltage means this is called as pole, right? And middle of this capacitor, right, voltage, if you measure this pole to this middle of the capacitor voltage point, middle of the capacitor point, then it is called as pole voltage. See, I have written. So these are the two capacitors. This point is O. Then what the pole voltage means? VAO. Pole voltage is VAO. Voltage between pole A and point O. That is pole A and point O. That is called as pole voltage. Next, VBO. This is VBO. This from this point to this point, then it is called as VBO, pole voltage. That means voltage between pole B. Pole means this point. Pole B2 and point O. This is called as one, and VB minus V0. Okay. Next, when the switches are on, you will get like this. When the switches are off, what is VAO? How can you get this VAO means? So that means when this switch is off, here what happens? Some voltage will be existed in between this point as well as this point. Therefore, VAO, this VAO is nothing but VAP plus VPO. Simple KVL, VAP plus VPO. For example, when this switch is on, what happens? This point is equal to this P, right? Then directly what happens? The capacitor voltage you directly can write on the answer. But when the switch off, the switches are off. This is open circuited. There is a voltage existed between A and P, and also again some P and O. So voltage is present. That's why VAP plus VPO. We will look into this. Don't worry about it. Right? So this is about the pole voltage. Simply what is meant by pole voltage is some this is nothing but pole. That is nothing but you can say that one point. So this is pole and to this pole. Okay. So this is A. You can say that this is A, right? Pole A, and to this point that is nothing but pole voltage, right? Next, now I want to clearly I will discuss. For example, when the switches S1 and S2 are on, this S1 is on, S2 is on, right? So for positive case, this is the thick line I have indicating. So this arrow mark doesn't mean that is a current direction. It's not a current direction, right? So the current always flows from A to B, right? Like this switch S1 A, switch B, and to the return path, right? Don't consider this as a direction. What is this direction? Is pole voltage direction. That means it is the point A to O. That is nothing but pole voltage, right? So now when this switch S1 and S2 are on, what is happening? See, this point and this point both are C. Therefore, what happens? P is equal to A. Then what is pole voltage definition? Formula I have given VAO from this point A to point O. That means in between A and O, what is the voltage? Vs by. So this is Vs by. Next, coming to VBO. So from this B to O. See, when it is on, what happens? It is shorted. Simply it is shorted. Therefore, this B point is equal to your M. So the voltage presented between this point B and O, what is the voltage? Minus Vs by 2. Because for B, minus negative terminal is connected. So that's why it is minus Vs by 2. So what is the voltage? Final, I mean load voltage. What is the load voltage? The load is connected between A and B. So therefore, what happens? VAB is equal to VAO minus VBO, right? So what is VAO value? Vs by 2 minus what is VBO value? Minus Vs by 2. Therefore, VAB is equal to Vs. See, in full bridge converter, when sorry, full bridge inverter, when S1 and S2 are on, the voltage, output voltage is Vs. When S3, S4 are on, the output voltage is minus Vs, which already we have discussed in single phase full bridge inverter operation. Okay. So the same thing, but we are going to implement with pole voltage, because for sinusoidal PWM technique, if you want to go for one way of representing, it is very useful. Okay. So this is the case for when S1 and S2 are on, right? So now, what is this? So what happens next when S3, S4 are on? So when S3, S4 are on, see this point, this is connected to this one, right? And this is connected to this one, right? This pole A is connected to here, and pole B is connected to here. Now, what is this P is equal to? See, because of these 2 points are short circuited, this B point is appeared here. Understand? Right. Next, again, these 2 points are short circuited. Therefore, N is equal to A. This point is directly appeared. Understand what I'm saying? Right. So now, what is pole voltage VBO? First we will go for VBO. That means the voltage between point B and O. What is the voltage here? PS by. Right. Next, VAO. So the voltage between A and O. What is the polarity here? Minus. Minus is connected to the A. That's why it is minus Vs by 2. Therefore, again, VAB is equal to VA naught VAO minus VBO, which is equal to minus Vs by 2 and minus Vs, which is equal to what happens? Minus Vs. So I told you in the previously already we have discussed, but in terms of pole voltage we didn't discuss. So this pole voltage concept is required. So that's why I'm discussing. So next one, sinusoidal PWM technique, which is nothing but sinusoidal pulse width modulation. So in that, what the first concept is bipolar pulse width modulation. So bipolar pulse width modulation. Second concept is unipolar pulse width modulation. What is bipolar pulse width modulation means? Just now we have discussed the pole voltage. You have VAO and VBO. So sometimes it is positive and sometimes it is negative. So that means bipole means what you can say that. So voltage may be positive as well as a negative. So unipolar means what happens is the voltage may be positive or zero, but not negative. So up to some first half second. So this is bipolar pulse width modulation. So that means first of all, a triangular wave is compared with your sinusoidal waveform. This is called as your triangular pulse width modulation generally, or sinusoidal pulse width modulation, you can say that. So because why we are calling sinusoidal means we are comparing sine wave with triangular wave. That's why it is sinusoidal pulse width modulation. So this blue color waveform is sine wave, which is called as reference waveform. Next, this waveform we are calling it as carrier wave, right? We are calling it as a carrier wave, right? So here for 1/2 cycle of the waveform, more number of carrier cycles are presented. So that we'll discuss later. Okay. So now here, what is the logic to generate the pulses for S1 and S2 as well as S3 and S4? It's very simple. If V reference is greater than V triangular or V carrier, both are same. See, carrier wave or triangular wave, just consider anything. Okay. So if V reference wave is greater than V carrier wave. Now look at here, this point. If V reference is greater than triangular wave. Now see, here your reference waveform is more than that of your triangular waveform. So because of that one, what happens? Your S1 and S2 are turned on. Okay. So even if you compare here, see this here. So your reference wave is more than your triangular wave, right? So that's why it is S1 and S2 will be turned on. Next, if V reference is less than V triangular wave, see here, this is V reference is less than triangular wave. See, triangular wave magnitude is higher, reference wave magnitude is lower. That means if V reference is less than triangular wave, then what happens? S3, S4 are turned on. Here, S3, S4 are turned on. Just now we have discussed clearly. When S1 and S2 are on, what is the output voltage? PS. When S3, S4 are on, what is the output voltage? Minus Vs. Right. Now see here, whenever your reference wave is greater than triangular wave, S1 and S2 are on. When S1 and S2 are on, what is the output voltage? Vs or VDC. Okay. Next, coming to here, immediately, right? So whenever reference wave is less than triangular wave, which device are on? S3 and S3 and S4 are on. When S3 and S4 are on, what is the output voltage? Minus Vs, right? So how you are getting this plus Vs minus Vs already have discussed in the previous videos. You just go through the single phase full bridge inverter, right? Just now with the help of pole voltage also I have shown you, right? So similarly for the negative half cycle also, right? So based upon the pulse, which one is greater? So S1, S2 are on, or S3, S4 are on, right? Now see, these are the pulses, right? Which is nothing but we can call it as a switching frequency, which is equal to carrier frequency. And what about this one? This is nothing but fundamental. That means useful component. So first component, B, you have B1, B2, B3, B5 there now. So in that B1, we are having fundamental component. This is called as fundamental component of output voltage reference frequency. Understand what I am saying? So this is fundamental component, and these are the pulses. See, this frequency is how much? 50 Hz frequency. Now, what is this frequency? Is nothing but carrier frequency. Whatever the frequency is given here for this to get this number of pulses, with that frequency only it will generate. So now you got idea what is the difference between switching frequency and fundamental frequency. So this is your fundamental frequency. That means after this pulses, if you use one filter, you will get the pure sinusoidal waveform. That waveform is 50 Hz frequency. But because of switching here, S1 and S2, S3, S4 are switching. So that's why we are calling this pulses frequency, which is called as switching frequency. Note that please, this switching frequency is not equal to your fundamental frequency. Switching frequency is different, fundamental frequency is different, right? Now, this is for when you are having less number of pulses, right? For example, if the pulses are increases, more number of pulses, these are, see, more number of pulses. So this is your VAO, this is your VBO, this is your output voltage, right? So now see, you know that when S1 and S2 are on, what is VAO is nothing but Vs by 2, right? If you want to can see, when S1 and S2 are on, what is VAO? Vs by 2. What is VBO? Minus Vs by 2, right? So now if you go for, see, so VAO, when here, see, when S1 and S2 are on, this is nothing but Vs by 2. So this is VAO. VAO is not, VAO is equal to Vs by 2. But when S1 and S2 are on, what is VBO? VBO is equal to minus Vs by 2. VBO is equal to minus Vs by 2. Okay, right. Next, when S3, S4 are on, when S3, S4 are on, what happens? VBO is Vs by 2. See, if you see, VBO is Vs by 2. When S3, S4 are on, VBO is Vs by 2. VAO is minus Vs by 2. So when S3, S4 are on, VBO is equal to positive. That means Vs by 2. And what is VAO is nothing but a minus Vs by 2. Right. This is with the help of pole voltage analyzation. Right. So now what is V0 is equal to VA0 minus VB0. Right. Now see here first, for example, if you consider this pulse, right? What is this? Vs by 2, right? Minus this VBO. So correspondingly here what happens? Minus Vs by 2 is there. Therefore, what happens? Vs by 2 minus Vs by 2, which is equal to what happens? You will get a positive Vs. Right. Let us go for another pulse. Let us go for this here. This pulse will go. Here what happens? This is minus Vs by 2. And here what is this one? Plus Vs by 2. Now what is the formula? So Va0 minus Vb0. Here what is here? Minus Vs by 2 minus of what is VBO here? Plus Vs by 2. So minus of plus Vs by 2 if you write. So you will get a minus Vs. Correspondingly you will get minus Vs. Now see, these are the switching frequency. This pulses on and off, on and off, on and off like this. These are switching frequency. Now how we are getting this fundamental, I will explain carefully, understand. It's very important. So now see, observe these three pulses width. These three pulse width is very higher compared to these pulses. Understand? In the negative half cycle, these three pulse width is more compared to these pulses as well as these pulses. So that means your fundamental waveform slowly started here. Whenever the pulse width is increasing, what happens? Your output voltage is also increasing. Simple duty cycle. In the duty cycle concept, what happens? If the duty cycle is increases, your output voltage also increases, like this. So duty cycle means what happens on time. So see, the pulse on time is increased here. So that's why slowly it is increasing here. Now see, here the pulse width is reduced here. That's why slowly this is going to be reduced. Again, here more pulse width, right? So that's why slowly the voltage will be increases here. Again, see the pulse widths are reduces here. That's why slowly it is decreases. Like again, it is increase. So this is nothing but fundamental waveform what we require. But these waveforms, these red color waveforms are switching frequency. That switching frequency is based on your carrier frequency. Okay. So for example, so let us say we just consider one frequency, let us say 300 or 500, just assume like that. But in the examination they have given like this, right? Then how can you find out this frequency? They will give sometime pulses, but they will mention what is this exact time and what is this exact time. Therefore, this point minus this point you can take, you will get one time period divided by not divided by. So this point minus this point, you will get some time. That you please inverse, then you will get definitely Fs values, right? That you place considered, but don't count every time this number of pulses. That will give sometimes wrong answer if you don't have any perfectness. So it is better to use always this value, this point minus this value, which will give your time period. Make it inverse, then definitely will get a carrier wave frequency. That is easy. See, in the examination, how you can write, so this is most important. So it is better to write when you are having less number of pulses compared to more number of pulses like this, right? So this is just I want to show you whether how the sinusoidal voltage waveform will be developed. So for that only I have considered more number of pulses. So for the examination point of view, just write down this one, it is sufficient. So if you write down by using pole voltage concept, it is better, right? So that's why I'm discussing it here, because in the standard textbooks, everybody they are using with the help of pole voltage concept. But generally, you already know when S1 and S2 are on, right? Output voltage is Vs. S3, S4 are on, output voltage is minus Vs. Like that also you can get it. But if you use pole voltage concept, it is better. So that's why I'm using. Next, what is frequency modulation ratio? Is MF is equal to, it's a ratio of Fs by Fr. What is Fs? Is nothing but carrier frequency. Fr is nothing but reference frequency. This reference frequency is always fixed 50 hertz unless until they mention anything. Sometimes if you refer Rashi textbook or some other high standard textbook, they will generally follow for a 60 hertz frequency, right? So it is better to use in our system 50 hertz frequency. In the examination, if they are giving 60 hertz, means you have to follow this reference frequency as 60 hertz. This carrier frequency may be anything. So 1 kilohertz or 2 kilohertz or 10 kilohertz, like that. So if carrier frequency is higher, means the number of pulses will be more. That's it. Okay. So, but if the number of pulses is more, what happens? What is the disadvantage? Is switching losses. See, the more number of times if your switch is on and off, means what happens? The switching losses are going to be high. That is the problem with this. If you increase the carrier frequency. So, but if you increase the carrier frequency, what happens means, so the lower order harmonics are reduced. Therefore, the filter size is reduced. At the end, we will go for the filter size. So the filter size is reduced. So that's why generally we are going for higher frequency like 10 kilohertz, like that. Okay. So this is about your bipolar pulse width modulation. Next concept, which is called as unipolar pulse width modulation. Right. So here in the unipolar pulse width modulation, we are going to use two carrier waves. I'm sorry, two reference waves. One carrier wave, right, and two reference waves. One is Vm sin omega t. Another one is minus Vm sin omega t. Another one is minus Vm sin omega t. So that means for Vm sin omega t, just you please make it 180 degrees phase shift. Then you will get minus Vm sin omega t. The logic I have written here. Okay. So here, if Vr is greater than Vc, then S1 is on. So this Vr is greater than Vc, then what happens? S1 is on. This total S1 pulses. S1 is on. So VR is greater than this VC carrier wave. S1 is on. Next, for example, if you take here, see here also, if VR is greater than VC, then S1 is on. Like next, if VR is less than VC, right? Let us take this point. Now here VR is less than VC. VR is less than VC. That means VR magnitude is less than VC. Then which one is on? S4 is on. See, this S4 will be on. So that means if this is on, if it is off. If it is off, it is on. Right? So simple. So because S1 and S4 are same leg switches, so that's why it should not on down both switches because of short circuit problem. Next, if minus VR is greater than VC, this is minus VR. So this minus VR is greater than VC. So this minus means this is minus 3. Let us say this is minus 5. So this minus 3 is your greater than your VC. So therefore S3 will be turned on. So once it is S3 is turned on means S2 will be off. Simple logic. So like that you have to go for the generation for the pulses, right? So very simple. You have to take one pulse like this, one waveform like this. So exactly 180 degrees phase shift, how to use this, right? So in the next class, I will show the simulation. There you will get the full sinusoidal waveform. If possible, today's class only we will see this how to generate this pulses. Okay. Next, here 3 modes of operation will be there. If you consider the positive half cycle, negative half cycle also 3 modes of operation. So if S1 and S2 are on, what is the output voltage is PS, right? So see here S2 is on, here S1 is on. So you already know that, you just know how to discuss when S1 and S2 are on, what is the output voltage? PS. Next, if S1 and S3 are on, what is the output voltage is 0. Now we will discuss this one, don't worry about it. And the similar fashion, if S4 and S2 are on, what is the output voltage is 0, right? So now we'll discuss these two along with this one, right? If S1 and S2 are on, what the output voltage is? PS, right? Now see, so when and S1 and S2 are on, these two switches are on state. These two switches are on state. Therefore, how the current will flows? Plus Vs, S1, R load, S2, and to the return path. Therefore, whatever the current you are getting, it is following your reference direction. Therefore, current is positive, developed voltage is also positive. Right, now here, most important thing is this neutral point. Okay, so and also the pole voltage, because a lot of analysis is there for this too. That's why we are going for this. So first thing is here, when and S1 and S2 are on, here S3, S4 are off. Right, you already know when this switch is off, what is the output, what is the voltage across this one is plus Vs. You please refer on my lecture, video lecture of regarding full bridge inverter. If you go through that, you will know that why we are getting this voltage across switch is plus Vs. I already discussed in the previous video lectures. You just go through it. So then you will get Vs here and here also Vs, right? Because this is collector, this is emitter. This arrow mark is nothing but emitter. So this is always positive. This is negative. Okay. So when these two switches are off, then what happens? This is plus Vs and here also this plus Vs. Now this point is A, this point is B. That means the load is connected in between A and B. So that is the load voltage. Now this is a neutral point, right? Now what is the voltage between A and N? Very simple. What is the voltage existed here? The same voltage will be existed in between VA and N. VA and N. So VAN is equal to what is the voltage here? PS. Next, what is VBN? Here I have written 0. Why VBN is 0? This is very, very important. See here, the switch is conducting means it is a short circuited. In short circuit, what is the voltage? 0. So that's why VBN is equal to 0. Okay. Next, VAO. What is VAO? The voltage between point A and point B. Now see, it is short circuited or not. See, S1 is conducting means it is shorted. That means simply this point is appeared here. Therefore, the voltage between A and O is nothing but Vs by 2. Right? See, if VAO is Vs by 2, obviously VBO is minus Vs by 2, which is exactly opposite. Right? Otherwise, I will tell you. So this is VBO. Now, what is this? Which is off state. Now, whenever the switch is off state, the voltage between VBO is equal to VBP plus VPO. That is the definition which I have given earlier. You observe here. So see here. So what is VBO whenever switch is off state? So here, sorry, VAO, VAO, if you just consider VAO. Therefore, what happens? VAP plus VPO. The same concept I am applying here. So whenever the switch is off, the voltage between these 2 points, VBP and also plus VPO, right? You know that VPO, what the voltage existed is plus Vs back. Here VBP, what the voltage is minus Vs, right? Because B is having negative. So that's why VBP is minus Vs, and minus Vs plus Vs by 2, which will gives you a minus Vs by 2. So if you have any problem, just go through this one. Very simple. If VAO is Vs by 2, obviously VBO is minus Vs by 2. There is no confusion, right? So like that you can go ahead, right? So finally, what is VAB? When S1 and S2 are on, you know that VAB is equal to Vs. So many times we have discussed. Otherwise, so VAO minus of minus Vs by 2, which will use your Vs. Or one more formula also. VAB, how can I write VAB is equal to VAN minus VBN. So Vs minus 0, which will apply here. VAB is equal to Vs. Understand what I'm saying? Right. Now we'll look into this. When S1 and S2 are on. So see this. This is S1. This is S2. This point. This is S1 period, and this is S2 period. Okay. So when S1 and S2 are on here, what is VAN? First of all, VAN is equal to Vs. See, when S1 and S2 are on, what is VAN? VAN magnitude is Vs. Understand what I am saying? When S1, S2 are on, that means this point, S1 and S2 are on, what is VAN is equal to VAN is equal to Vs. This magnitude is Vs. Next, what is VBN? 0. That means this period is 0. This period is 0. Okay, VBN is equal to 0. Next, what about VAO? VAO is nothing but Vs by 2. See, in this period, when S1 and S2 are on in this period, what is VAO? VAO is nothing but Vs by 2. And what is VBO? Minus Vs by 2. See here, VBO is minus Vs by 2. See, this VAO is exactly opposite to this Vs by 2 when S1 and S2 are on state. Understand what I am saying? So that I have shown clearly. So VAO is equal to Vs by 2 and VBO is equal to minus Vs by 2. So here when S1 and S2 pulse is on, VAN is Vs, VBN is 0. This VAO is nothing but plus Vs by 2, VBO is nothing but minus Vs by 2. And finally, what is the output voltage? Vs. That V naught is equal to here. See this S1 and S2 are conducting. Understand what I am saying? So this is the way to analyze this one. So next one, when S1 and S3 are on state. When S1 and S3 are on state. Now see here, VAO, VBO both are Vs by 2. I told you clearly this is valid. Opposite is valid when S1 and S2 are on state, because this is related to one leg and this is related to one leg, but opposite arms. I mean, this is upper switch and this is a lower switch. Understand what I am saying? For example, if it is also upper switch, what happens? You will get plus Vs by 2 only. So now we'll discuss that one. So when S1 and S3 are on, see this is on state, this is on state, this is shorted, right? So therefore, once it is shorted, what happens? This A point is appeared here. Therefore, VAO is equal to plus Vs by 2. Similarly, when this is short circuited, this point is appeared again here. So therefore, when VBO is equal to Vs by 2. So VAO is Vs by 2 and VBO is Vs by 2. So different legs, both are positive related switches. So that's why you are getting magnitude is Vs by 2. Next, VAN. See here, these two switches are off state. When it is off state, what happens? I told you that the voltage magnitude is Vs. Here also it is Vs. So that means what is the voltage between A and N? So Vs. Right. Next, what is Bn? B and N. What is this voltage? Vs. Right. Therefore, what is VAB? So you can go for these two these two expression or these two expression, anything. VAB is nothing but VAN minus VBN. Therefore, VS minus VS is equal to 0, or VAB is equal to VA0 minus VB0. So what is VA0? VS by 2 minus VS by 2. Both are zeros. Now we'll see S1 and S3. When S1 and S3 are on, see here this pulse, this one. When S1, this is S1 pulse, this is S3 pulse. When S1, S3 are on, what is VAN? Is nothing but this one. VAN, this is VAN, this one. VBN also, this one. Okay. So next, what is VAB? VAB is nothing but 0. See, V0 is nothing but VAB. What is V0? VA0? VS by 2. See, VA0 is VS by, and VB0 is also VS by 2. So this is S1, S3 corresponding E. Please check the things. Understand? This is the case for mode 2. Next, mode 3. What is mode 3? S2, S4 are on. Right. That means lower switches are on. Again, lower switches are on means polarities are same. Remember that, right? So now, what is VAN? So when the polarity, when these two switches are on, when these two switches are on, what happens? The voltage between these two is 0. This is also 0 because of dead short circuit, right? So now upper switches. The upper switches, what are the upper switches? Off state. What is the voltage existed? Vs. Okay. Right. Now, once these two switches are on, right, VAN is 0 from VAN 0. Similarly, VBN, which is equal to 0. What is VA naught? So this is A naught. What is VA naught? Right, VA naught is equal to minus Vs by 2. I told you. So what is when it is off? This voltage minus this voltage. That means minus Vs plus Vs by 2. If you apply the KVL like this path, KVL like this. So because A is connected to minus, that's why minus Vs plus Vs by 2. So that's why what happens, you will get minus Vs. So because of both switches are off, you will get same. Right, now we'll look into this. S2, S4 are on. So see here S2, S4. So where S2 is nothing but, see, this is your S2 pulse and this is your S4 pulse, right? So when S2, S4 are on, so this one. So what is VAN? 0, VBN 0, right? What is the output voltage also? 0. Understand? See this pulse. So S2 and S4, this part as well as this part, right? Of course, here your two devices will conduct only this period from here. Okay, so exactly from this period. So VAN is 0 and VBN is also 0. Therefore, output voltage is 0. What about this VA0? Minus Vs by 2. See, VA0 is equal to minus Vs by 2. VB0 is equal to minus Vs by 2. Understand what I am saying? So you just consider S4 pulse as well as S2 pulse. You may consider some other place also. You may not consider only this place. That's why I didn't draw any exact curve, because you have to consider all the wherever you want to flexible. Just consider that. Okay. So this is about this one. Now, if you observe these three modes of operation, first mode of operation, what is the voltage? VAB is equal to Vs. That means this one. Second mode of operation, what happens? VAB is 0. That means this one. Okay. So this one, S1 and S3, I mean S1 and S3 are on means this pulse. So this one. Again positive, again 0, again positive, again 0. This is called as unipolar pulse width modulation. Negative we will see, right? So in case of bipolar, if you see bipolar pulse width modulation, what happens? See the output voltage positive, negative, right? In case of unipolar, first half cycle, if you consider some pulses, positive 0, again positive 0, like that you will get the output voltage. Okay. So, and when you are coming to the negative, see, actually when you will get negative voltage, when your S3, S4 are turned on, you will get the negative output voltage. Now we'll see this S3, S4 are. So mode 4, when S3, S4 are on. So we'll check this somewhere else. So here, just check this one. When S3, S4 are on. So this point, this one second. This is S3, this is S4. So this period, only this period, your switch is on. So when S3, S4 are on, right, what happens here? So see, when S3, S4 are on, so first of all, the current will flow plus Vs through S3, S4 and to the return path. Now this current is opposite to that of your reference direction. Therefore, current is negative. V0 is minus Vs. Okay, so that is the case. Now what is VAN? If you see, because this switch is short circuited, the voltage between these 2 points is 0. Next, what is VBN? VBN, what is VBN is minus VS. VBN is VS because it is off state, therefore it is VS. Next, what is VAO? Yeah, the VAO. If you observe this point, VAO. Now A having negative polarity, see this negative polarity is connected here. So that's why this minus Vs plus Vs by 2, which will give your minus Vs by 2. Next, what is VBO? See, this is shorted. Immediately, this point is appeared here. Therefore, VBO. What is VBO? If this point is appeared here, means VBO is plus Vs by 2. Okay. Now, what is VAB? So, VAN minus VBN. Therefore, 0 minus Vs is minus Vs. Or you can write, check this one. VAB is nothing but VAO minus VBO. What is VAO? Minus Vs by 2. Minus this plus Vs by 2, which will give you a minus Vs. Now we'll consider this point, this one, S3, S4 pulse. Therefore, first of all, what is VAN? 0. VAN is equal to, where is VAN? 0. VAN is equal to 0. Next, what is VBN? So this is VBN. VBN is Vs. So this pulse is S3, S4. Just consider this period. Okay. So this one. That's what I'm saying. VBN is Vs. VAN is 0. Next, what is the output voltage? Minus Vs. See, only this period, if you consider this period, just getting minus Vs. Right. Now, what is VA0? VA0 is equal to minus Vs by 2. VA0 equal to, see, this is minus Vs by 2. I have written here minus Vs by 2. Similarly, what is VB0? Plus Vs by 2. This is plus Vs. See, opposite legs. Because of opposite legs, one is negative, another one is positive. Right. So, I have given the pulse cycle here. You may consider anywhere in the waveform. Don't consider only single place. Just check with the different places also. Here, what is our observation in the unipolar pulse width modulation? Here, positive off cycle, up to some time you will get positive pulses and 0. After some time you will get negative pulses and 0. So in this, see here in the negative, sorry, here this is the negative half cycle. It's not positive half cycle. Correct it. Please check it. This is the negative half cycle. In the negative half cycle, if F3, S4 are on, minus Vs. This already know. These two conditions are same as that of these two. So that's why I am not going to repeat again. I already covered these two. Okay. So now if you observe this waveform, see, up to 0 to this period, you are having positive output voltage, and up to here you are having negative output voltage. Here, because of this, what is the advantage? If you consider compared to this one, if you compare to this bipolar, unipolar having more output voltage frequency. Frequency of output voltage is, switching frequency of output voltage is higher than that of bipolar. Therefore, filter size is reduces, harmonics are also reduces. That's why in some cases we are going for unipolar concept, right? Because output switching frequency of output voltage is high. Switching frequency of output voltage is higher. See, the number of pulses is higher here compared to here. If you see, this is one pulse here, right? So here what happens, more number of pulses you will get here. So I will show in the simulation, then you will get more clarity. So this is the advantage of going unipolar rather than that of bipolar. In bipolar, what happens? What happens is it is switching from plus Vs to minus Vs. Here what happens, it is switching from plus Vs to 0. Therefore, error is reduced here. Therefore, harmonics are also reduced. In case of bipolar, this is plus Vs minus Vs. So the error is more. When you are switching action, the error is more. When because of this switching action, more losses are there. Because it is changing from plus Vs to minus Vs. Whereas here, it is changing from plus Vs to 0. Therefore, switching losses are reduced and error is also reduced. THD is reduced. And because of higher output frequency, then what is happening here exactly for higher output frequency, the filter size is very less. So because of all these advantages for single phase inverter, so generally unipolar is preferable. Okay. So this I have completely discussed about unipolar and bipolar, and this is some other comparison. See, in case of this here, first one. So here a triangular wave is you will get some up to sometime positive, another one some to sometime negative. So here in this is one type of PWM, right? Then what happens here? Uh, two both are same, but see here triangular wave is at zero. Here the triangular wave starting point at peak. So this one frequently asking question for the 1 mark question. When the triangular wave has its peak coincident with a zero reference, whenever this peak value is coincident with zero reference, then the number of pulses per half cycle is NC is equal to FC by PFR. FC is carrier frequency of triangular wave, FR is reference frequency, right? So that is the thing. For example, when these two coincide at the same point, that means zero crossing of reference wave, zero crossing of carrier wave, both are at what happens? Both are at same point. Then what happens is NC is equal to FC by 2FR minus 1. Now see here how many pulses are there? 5 pulses. Here only 4 pulses. FC by 2FR minus 1. This is FC by 2FR because one pulse is reduced here, right? That's why you are getting 4 pulses. Understand what I'm saying? Now I will show just this MATLAB simulation. I will try. First of all, yeah, 1 second. So in that, yeah. Uh, so this is unipolar pulse width modulation. 1 second, just I will run the simulation. So see here, two carrier waves. See, this is one reference wave, another reference wave. This is one carrier wave, this is another carrier wave. This is 0 degrees, this is 180 degrees. So that pulses is given to S1 and S4 like that. Okay. So here more number of scopes are connected because to monitor all the waveforms and all those things. Right. Now I want to show you this output voltage waveform, not output voltage waveform. Yeah, output voltage, some switching pulses also, right? So, so if you consider this, yeah. So, so these are the switching pulses: S1, S4, S3, and S2, and this is your output pulse. Now see, up to sometime it is positive, up to sometime it is negative. Therefore, the switching frequency is output frequency is higher than that, higher than that of your bipolar scheme generally. So that's why we are monitoring this one. And I want to show again. Yeah. This is, if you observe, so this is the screen, 180 degrees phase shift. So this is 0 degrees. Let us say this is 0 degrees phase shift, and this is 180 degrees phase shift exactly. These two waveforms we are comparing. That is generally unipolar concept, right? And this is the output voltage concept. The output voltage switching frequency, output voltage. This is the output voltage switching frequency. Okay, right. So analysis is also important. Just I want to show what is exactly unipolar. So here, see, this is the generation of pulses of carrier frequency, and this is also generation of same will get. Here I am using this 15 pulses. That means by divided by 15 means you will get 15 pulses per full cycle. So once 15 pulses per full cycle means, right? So here 15 pulses per full cycle. Now if you count here, right? So how many pulses? So exactly, yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is half cycle only. But what I have given here, uh, here what I have given, this is 15 pulses per cycle only. Okay, to take this is 15 pulses per cycle. But in the output waveform, just now what I have shown, so in the output waveform, just what I have shown, that is 15 pulses per half cycle. 15 pulses per half cycle. Now I think you got the point exactly. So now what is our conclusion is the output frequency, the output switching frequency is higher than that of your bipolar, right? So in the next class, what we are going for, we will go for some analyzation, some mathematical concept is important. Now, here we didn't find any output voltage, right? In the next class, we will discuss that. So see, this is unequal voltage pattern. Your pulses is unequal voltage pattern. For this, how the Fourier series we have to take, right? And bipolar pulse width modulation simulation and some output voltage equations for pole voltage, average output voltage, and all those things. This amplitude modulation ratio also I will discuss in the next class. So this is about sinusoidal pulse width modulation. If you have any queries, just ask me. Definitely I will help you. Thank you.